Okay, in today's class, in today's lecture, we are going to talk about the classification based on the operands, based on the operand mode, operands addressing mode. In the ISA design, we just following. The first one is the ISA classification, and the design is based on the operands, where the operands are stored. And we have talked about this with various examples, like how those operands are stored in the different format that we observed in the previous class. That the standard structure, and how these operands are there. So based on that, we just observe the classification and stack, and then we see some of these examples. So today we are going to talk about the ISA classification based on operand addressing modes. So as we know that the operands can be stored either the memory which is within the central processing unit CPU, that is in registers, or in the memory location, that is we call the memory location we call the RAM, right? So based on that, if the operands are within the register, then what will be the instruction design, and if the operands are in the memory, then what will be the instruction design that we have observed. So today we see based on the addressing modes. So this addressing modes specifies how the operands are located from memory or from the registers, from memory and from the register, the combination of this one. So there are the common addressing modes which the standard ISA follows, that the register addressing mode, immediate addressing mode, register indirect, displacement addressing mode, indexed addressing mode, direct addressing mode, memory indirect, auto-increment and auto-decrement, and the scale addressing mode. So let us see this one by one. What is the common register addressing modes? So as we saw in the previous examples, in register addressing modes means the operands are the located in registers itself, itself. So these registers, we observe that the registers we use are general purpose registers. So we use R0 to R15 registers. So the operands located in R0 to R15 registers, or we can write it as your R1 to R16 registers too, right? So when the operands are in the registers, then if you have the operations, arithmetic operations, to design of arithmetic operation instruction set, like R1 is equal to your R2 plus R3. That means the destination as well as your source 1 and your source 2, both are in the register itself, the operands. That means if you have the equation in C language or any high level language, like A is equal to B plus C, so B will be in source 1 and C will be in source 2. Whatever the operation, ALU operation performed, that will go and store or load in A. So for that, if the operation we find this R1 is equal to R2 plus R3, then the addressing mode instruction, the ISA instructions are, we can write it as the common format which we are following. It follows the opcode first, then the destination, then source 1, then your source 2. So in this case, in this operation, the operation is addition operation, the arithmetic operation. So the mnemonic which you use, the add, and the destination is R1. So R1, and source 1 is R2, and source 3 is R3. So that is the instruction of your register addressing mode. Suppose in some cases the instruction comes the direct constant value is supplied to the operations. So there, whether one operand is a constant value, we call it as the immediate addressing mode. In this immediate addressing mode, we will find the assembly instruction, the operation as your R1 is equal to R3 plus your constant direct. So here the memory, the registers are not used, the direct, the constant value is used inside. So then the instruction is written as your opcode is your add, because we are doing the addition operation. Then your destination is R1 register, and then your source one is R3, and your source 2, the second operand, the second operand is direct constant value. So you are giving the constant value, we call the immediate one. So immediate addressing mode. Another addressing mode is register indirect. Register indirect, as known as your register deferred one. So what it means in register indirect, it is accessing an operand whose memory address stored in the register. So as we are saying that the registers are in CPU, but the operand is reside in the RAM, in the memory somewhere. So whatever the address is there for that RAM, that address is stored in this register. So when it is referred to the address, then it is going to that address location, fetch this operand that we call the register indirect. Register is not containing the operand directly, it is containing the address of the operand. So it is often used in the high level language C, where C pointers are used. For example, assume the address of the second operand is in the the address of second operand is in your R3 register, then how it can be written, right? So it can be written that for the first operand will be available directly in R2, but the second operand address is given. So for that address, it is written as R3. So in R3 register, the address of operand is there. So by using this star, that operand will be fetched. So what is the instruction set for that kind of operations? For the register indirect one, the opcode is the operation addition, then destination is R1, for source 1 is R2, and source 2 is R3. R3 is giving the address of an operand, so we write them it in the square bracket. So this is the instruction for register indirect. Then comes to the displacement addressing mode. In displacement addressing mode, it is accessing an operand whose address is computed based on the base address and an offset, or we call it as your displacement. So what it means, this displacement generally we find in the stack operations or in stack operations. So stack is a special purpose register on the CPU itself. So those stacks, you'll find the stack operation, or generally if you refer it as your memory, in that memory it consists of the base address where it starts. For example, 1002, 1004, and so up to 10, some n, suppose values, 100 n values. In that case, it takes the base address first, and then if the element is somewhere, then whatever the distance is there, that we call is your displacement or the offset. So in this case, assume that the base address is stored in the register. And for that base address, whatever the displacement is there, offset is there, that will be added to find this second operand. So for first, what happens? The address of an operand is calculated as, or the evaluated as, base address plus its displacement. So base address plus displacement, as we say that R3 holding the base address. So that gives the address part of your element. So that address part can be represented as your star address. From there, you need to retrieve the operand. So the operation can be written in the displacement addressing mode. The operations looks like your R1 is equal to R2 plus the address, where the address R2 plus your address, where the address is your address is equal to the base address plus the displacement. Here 100 is the displacement. If it is written 10 means 10 is the displacement. If it is written 50 means 50 is the displacement part. So then for this kind of the displacement addressing mode, the instruction design can be done that here the operation is addition operation. The opcode is your add. Your destination is R1. So you write the R1, and your source one is R2, and your source 2 is the second operand which is available in the address. That address consists in the register R3 with the displacement 100. It gives the address of that one. From there it can be retrieved. So this is the indirect the displacement addressing mode. So then comes to indexed addressing mode. In the indexed addressing mode, it is very useful for accessing an element of an array in the memory. So generally when you are arranging the elements in an array, it may be single dimensional array or it may be double dimensional array. It will be represented with the name and the number of elements in that. Number of elements. So the beginning address, in this indexed addressing mode, the beginning address and the offset of your element are stored in the register. What are the? One is beginning address, another one is offset. So for them, the different registers are used to store the beginning of the address. One register is used to store the offset of the element. Another register is used. So for example, consider here is the summation with the x of 5 elements as an operand. Suppose the fifth element operand, then the instruction the operation can be written as your R1 is equal to R2 plus the second operand is in the array of your fifth element. So what happens? Assume that for this purpose, assume that this is an array. So first you need to store the beginning address in one register. So assume that R3 has the base address of your x, the starting address, and the another register R4 has the offset which stores the offset of an element. So consider, let us, this array is an integer type, means it holds only the integer values. The size of array is suppose 10 elements. Then in this array, the first base address is set the beginning address of your array x to the R1 register. So it can be written as the base address stored in or load into your R3, and then in that you are going to summing the 5 elements. So that fifth element, 5 elements will be there. We are following the integer. So integer size is 4 bytes. So it is multiplying how many bytes of the offset is there. So 5 into 4. So the operation can be written here as the second one is in the memory. So address is referred. So it is written as your R1 is equal to R2 plus the second operand is base address plus the total size, that is R4, that gives the complete address of your second operand. So the instruction will be written as the add operation. Destination is R1, source is R2, and second operand or second source is in this address. So it is written in the square bracket, right? Right. So the next one is the direct addressing. The direct addressing mode. In direct addressing mode, instead of supplying the value, it is giving the address of the operand. So when the memory address of an operand is known at compile time, that is the value of the address is known, that is the value of the address is known at the compile time. So this is typically used for the loading static and global variables in the program. So for example, assume that there is one operand and whose memory address is at 1000, then the operations, the operations to convert this address into to locate the element, this address will be stored in the address variable, and that will locate the operand. So it is constant one. So the operation can be written direct to addressing mode. The operations can be written as R1 is equal to R2 plus star of your address, which gives the address, direct address. So here you are giving like immediate value, you are giving the immediate the address here. So the operation here is addition. Destination is R1. Similarly, source one is R2, whereas your address is represented in terms of square bracket, the direct addressing mode. Right? Then comes to the memory indirect. So as you know, as known as the memory is deferred, this is called your memory direct. What is happening memory indirect one? When the operand is accessing and which is having the nested pointers, then we use the memory indirect addressing will be taken into the consideration. So example for that is assuming that the first address of an element or the first address of an operand is in R3, then the operations can be written as your R1 is equal to R2 plus there is a memory, that memory location is consists of the memory of an operand, that where the operand is located. So that is memory indirect. So for example, in this RAM, as we saw in previous cases too, if the operand is in this location, the address is given that 1002, 1004, 1006, 1008, 1010, 1012, suppose. So then if the first address, the base address says, the first address is, in 1010, it holds the address of 1004. So first it goes to 1010. In that 1010, it finds 1004. Then it goes into 1004, the first memory. That memory consists of another memory address. In that memory address, the operand is available and the element is available. We call it as your memory indirect. So that is written as the R3 is holding the first address of the operand that's stored here, and that will be given. So this R3 is holding the address of, so double addressing is there. So that will be written in the instruction as in memory indirect instruction. It is written as the X in this bracket in R3. If it is single address, direct addressing, or in that we write it in our square brackets. But if it is having address of address, then it is called as your memory indirect address. So then comes to auto-increment and auto-decrement. So this auto-increment and decrement, they are useful when stepping through an array, as we discussed. When stepping through an array, so when you are trying to access this array of elements, either from right to left or left to right, it steps one step. First element will be accessed, then second element, then third element, and so up to n elements. Or if it is somewhere in between middle, then it may go front and back. So auto increment will be done and auto decrement will be done. So the address of the current element in the array, which is stored in an array or in a register, and this register is automatically incremented as the code proceeding to iterate over every element in the array one by one. So for example, assuming that the beginning address of your array X is in the R2, the beginning address of your X is in the R2. So that can be written as, here consider this array as your integer type. So that means it takes 4 bytes. So then the beginning address will store in R2 as said first. So then this, the accessing this array is continued until it reached to the end. So for that, the while the while code will be written in C language as while true, then increment the register R2 value, increment the register R2 value by 1, and it advances with the 4 bytes because we are using the integer type. So the address of your base address of your array is stored in your R2, and that will be incremented and stored in register R1, and this loop continues. So this R2 will be incremented with advances with 4 bytes because we are using integer. If we are using, suppose, the double here, double integer, in that case it will be increment with 5 bytes, sorry, 8 bytes element. That depends. So when we talk about scaled one, we talk about this one. So if this kind of operations are there, then the instruction with the loop, it gives instruction with this kind of loops given as the operation is your addition operation because you are adding, every time you are adding 1 plus 1, 2 plus 1, 3 plus 1, 4. So every time addition operation is happening, so add R1, so add the content of R1 with the increment R2 base 1 and store result in R1, and it continues until, and it goes to the go to loop. So similarly, in the auto decrement, instead of add, it uses the subtraction. So this auto decrement is similar, except the address is automatically decremented part. So the last addressing mode is we call the scaled addressing mode. In scaled addressing mode, you can see we have the different data types will be there. So this scaled addressing mode is used to access an array element. So up to now we discussed that there is an array of certain elements, start from 1 to n minus 1 or something like that, and we define that this is integer. So the size of integer is 4 bytes, so all the elements which occupies in this array are same. But so by this scaled one is used to access the array elements with the array's base address as we discussed, and the element is index and the size of your element, that is scale. So what is the size of element? This arrays can handle any type of element such as the characters, integers, floats, or doubles. So assume here that, assuming the beginning, as said in the arrays or in stack, the beginning address will store in separate register, that is R3. So here we consider the double integer, or the double, we can say in that double it takes 8 bytes, and this is an array. So the base address of array will be stored in one register, okay, and then it start accessing the other elements by following the size of your element. So the operation here is basically, the operation is given like this: R1 will store the value of the content which is added in R2 plus the elements of your X, that is 10 elements. So what it means, first base address is stored in R3 to calculate the address of the second operand. Base address is stored in R3, and R4 consists of total 10 elements. Okay, so that is the offset. So it gives that the element index and the size of the element. So this will be written as your R2 is equal to R3 of your R4. R3 is X and R4 is your 10 in the square bracket. So then it will be written as your, here is the addition operation. So add operation, source is, destination is R1, source 1 is R2, source 2 is the base address plus the offset element, that is multiplied with 8. Why? Because we are using double. If it is suppose integer, then it is multiplied with 4. Okay. So a double takes 8 bytes here. So this is the scaled one. So these are the different addressing modes which are used to design the ISA, and based on that the classification can be done. So that is, one is register. So the operands are available, are located within the register only. Immediate means one operand will be in the register, another operand is direct value, is a constant value is provided. In register indirect, the second operands, or one of the operands address is mentioning. Then displacement gives the offset. Then index is also gives the offset and base address. Then direct addressing gives the direct address value. Memory indirect is the address of the address. Auto increment and auto decrement used in arrays to increase and decrease. And in scaled addressing modes, the same array can able to hold the different kinds of data types. So these are the classification of your common addressing modes. So now see the complex addressing mode, okay, which can cover most of our addressing modes which we discuss now. Consider a two-dimensional array. So that is X of your 10 by 10, the two-dimensional array. So that is holding the elements, that is capable to hold the elements of your 10 by 10 elements, and which is in the size double, the size in double. That means every field holds 8 bytes, means every element holds 8 bytes. This, right? So what it in this two-dimensional, consider the elements of two-dimensional array, which is use the operands. So in this case, if the operation is given that add the content of R2 with the element, two-dimensional element of your X, which is at the location third row and your fifth column, and store that value in R1. So then what is the instruction design process for this? So it consists that, as we know, the arrays, the location of your this is calculated first. So this is calculated as the base address from where it started, the base address plus 240 plus your fifth element with 8 bytes. How? That means this value, the X of 3 comma fifth element, that starts from the fourth row, and the first 3 rows occupies 3 rows of 10 elements per row, which is multiplied with your 8 bytes. So what it happens? The total 8 bytes and the total number of elements will be given the 240 bytes, the occupies of this one. Another one is this element, the X of your 3 comma 5 is the sixth element on the fourth row, therefore it starts after the first 5 elements, that is 5 elements multiplied with your 8 bytes. So in other words, the offset or the displacement for the fourth row is 240 bytes, and the index is 5 within the fourth row, and the element size is scaled is your 8 bytes. So that gives the complete address of this X1. So that to write the instruction for this element, it uses the addition operation. Source destination will be R1, source one is R2, but we focus on this double, the two-dimensional array. In two-dimensional array, it first consists the base address, that is X will be there here in base address, and then the index part, the index address will be stored in R4 with the 8 bytes scale, and then the displacement, the location of that, the operand. So this addressing mode consists of base, index, scale, and displacement. Base, So that gives the addressing mode, index addressing mode, scaled addressing mode, and your displacement addressing mode. So this is the memory addressing mode which is used by your 8086. So this addressing mode can replace or include most of the addressing modes as we just discussed so far. So then another way of designing or classification of your ISA is based on the instruction length. Based on the instruction length. So in this instruction length, the instruction maybe give the arithmetic instructions, logical instructions, control instruction, storage instructions. Okay, in storage instructions, simply it writes A is equal to 2. In control instructions, you use the jump conditions, conditional jumps and unconditional jumps. In arithmetic, they use the any operation that perform that A is equal to B plus C. Okay. In logical operations, they require two bitwise operators like 0 and 1 or 0, like that. So what happens in this case? See, in this instruction, 3 operands are there. In this instruction, only the one operation is there, one operand is there. Here, only 2 operands are there. That means the instructions are, sometime if you are going to perform only addition operations, it requires the 3 instructions. Sometimes if you are going to performing the storage operations, it requires only 1 operand. If you are performing control, it requires 3 or 2 or 3 operands. So that depends. So the instruction length, based on this instruction length, how the ISA can be designed. Right? So in this, instructions are eventually encoded with zeros and ones in the instruction what the instruction length classification. That means if I have a instruction like add instruction is there, and the name for this add is sequentially given that this is 1, so then it can be written as 0 1 by using 2 bits. But if you are using 8 bits register, then the rest of the bits will be filled with the zeros. So that we call the encoding, that we discuss in the computer arithmetic in the coming series. So, but here you just remember the instructions are eventually encoded with zeros and ones. So each instruction is encoded into several bytes of binary numbers, as we said. So based on that, there are 2 types of ISA in terms of the instruction length. We call the variable length instruction set architecture and the fixed length instruction set architecture. So the choice in encoding that affects how hard it to decode. Encoding is easy, but decoding them, so it was some sequence of instructions are going to be executed. First instruction, if it is requires only 8 bytes or 8 bits, 8 byte length. Second instruction, suppose only 4 byte length, in that case it is hard for processor to predict what is the size of the next instruction. So decoding is important. When we talk about this instruction execution, there we see how it is divided into 2 parts and they are executed in the decoding phase. So the choice in the encoding affects in the decoding part. So how hard it is to decode and streams of bytes back into an instruction, and how much memory space a program can take in the variable length instruction and for the fixed length instructions. Okay. So that in the variable length instructions, generally it is used by the processor called VX processor of your architecture 8086. So variable length instructions require some multiple step fetch and decode, fetching and decode, but it allows for much more flexible and compact instruction sets. Compact instruction set. How? That means it requires low on memory uses. Suppose we are having the 2 instructions here. Here adding instruction and move instruction, suppose. Or simply we can say adding C is equal to A plus B. That means to store this instruction, it requires, to hold the destination and your two operands and the operation. So 4 fields are required. But whereas if we say that store A is equal to 2 only, so in this instruction, it is simply a, store the value 2 into A only. So instruction length is reduced. When if you are using the fixed instruction for this instruction also, for this it requires 4 fields. For this also, it reserves 4 bytes of memory. I mean the 8 bits of memory, but instead of it may take only 2 bits. So if you are using variable length for the two operands of instructions, it can hold longer memory. For one operand, it can hold the shorter memory. That is, low memory uses will be there with this variable length instructions. Since many simple instructions only use 1 or 2 bytes only, as said, but it is very hard to decode. Very hard to decode. Encoding is easy, but very hard to decode, because one instruction is using 1 byte, another instruction is using 2 bytes, another instruction is using 1 byte. So it is difficult. So to decode needs to first determine the length of next instruction in the memory before decoding it. So for example, in this 8086-64 bit, it is taking that for encoding this instruction, add R12 and R11 and store the result in R12, it may take, which has 3 bytes only, because it is having 3 bytes only. But whereas encoding the move instruction, it requires 4 bytes. So that is the difference in the, and we call it as your variable length instruction. So in fixed length instructions, the fixed length instructions allow the easy fetch and easy decode, because the size of your instruction is constant, 0 to 8 bits. Suppose all the instructions fit in this one only. So the decoding, during the decoding of your instructions, there is no need to determine the size of the next instruction. So that's why the fixed length instructions allow easy for fetch and decode and simplify pipelining and parallelism. How they are easy to decode? Reason is there is no need to determine instruction length, as each instruction always has the same length. And this fixed length instructions take more space. Reason is, if the only 1 byte required instruction is there, even though the space will be reserved 2 bytes for that. So as the length of the instruction is determined by the most complex instructions. So for example, the fixed length instructions, okay, the variable length instructions will be used by this, generally using by this, the architecture 8086 VX. But whereas the fixed length instructions are used by MIPS technology, millions of instructions per second technology. So this MIPS instructions are always 32 bits in size. Instructions always in 32 bits in size. So that the instruction 32 bit, out of 32 bit, the first 6 bits will be used for your operation code. The 6 bits total were 0 to 31 bits, okay, and the remaining 26 bits will be used for the operations. Operands means your source or destination one, or your, we call the operands source or destination one, source or destination two. So it says 6 bits for the opcode and the rest of the bits for your operands. Another, the example is the standard ARM architecture. So this ARM instructions also use 32 bits with the variable length for the opcode. Sometimes it may use 6 bits, sometimes 9 bits, sometimes 4 bits, sometimes only 2 bits. So that is variable length. If it is using the 4 bits, that means the remaining bits are used for your operands. So that is variable length. So how many operands, from just summarizing, how many operands are required for designing an instruction means most instructions have 3 operands, at most 3 operands. One is destination, source 1, source 2, and at least one operation. Along with this, there is a load and store. Store and load will be there of your assignment operations. So most ISS specifies 0 to 3 operands. As we said, if you are using addressing mode, then there will be only 2 operands. I mean, the explicit operands per instruction will be there. So these operands can be specified implicitly or explicitly. If you are using accumulator or stack, then they are implicit one. If you are using registers or memory address, they are the explicit one. So an accumulator styled instructions uses the destination implicitly as a source operand, but generally only one operand can be from the memory. So based on them, the ultimate classification done after lots of the debates on these instruction set designs. As we have seen, there are many ways to classify based on operands, based on the addressing modes, based on the instruction length. So there is one classification that considers most of the features we discussed in previous, the previous slides so far, which includes two class of ISS. We call them as two class of ISS. We call them as CISC and the RISC. CISC is the complex instruction set computers, and RISC is reduced instruction set computers. So this CISC, they use the variable length instructions, variable instruction length, whereas RISC use the fixed instruction length. So let us see what is CISC and what is RISC. Let us see what is CISC and what is a RISC. Right. So to design these instructions either in the CISC or the RISC, what leads to the good ISA or bad ISA? What leads to good for ISA and what leads to bad for ISA? So there are three things which should be considered for which leads to a good ISA is ease of implementation in the processors, that leads to a good of your ISA, as well as ease of programming in terms of programmers, in terms of the hardware. Okay, so ease of programming and the future compatibility. So the ease of implementation means, does the ISA lead itself to efficient implementations to design the hardware and execute the instructions? And another one is ease of programming means, can the programmer or the compiler use this ISS effectively? Or the future compatibility means, as from ISS may last 30 years, as technology developed, lot of development is also increased. That means whether it will be compatibility, giving the future compatible for special features or addressing range. Earlier days it supports only the 8 bits, then 16 bits addressing range, then 32 bits, and nowadays we are using the 64 bits addressing ranges, etc. That need to be the thought of. So let us see these one by one of your CISC and RISC of your ISA. So in implementation concerns, of your ISA of your CISC or your RISC and your RISC, in this case, in implementation point of view, means in terms of the hardware, it must be simple decoding, so that is easy for implementing. Simple decoding means it use the fixed length instructions. So in the fixed length instruction, the instructions are encoded with zeros and 1 bits, as we said, and every instruction has the same length. For example, if we have the 32 bit the instructions, as we said, so every part of the instruction takes the same bits. So for example, first 8 bits always represents the opcode, next 8 bits for destination, next 8 bits for the source, and next 8 bits for the destination, I mean the second source. So that is easy for implementing. So the hardware which is required to execute this opcode, destinations, the source, and your the resource source 1 and source 2 is fixed one. So most of the reduced instruction set ISS they design, their implementation is very easy, such as your MIPS and ARM, they have the fixed length instructions. But it is very simple to do decoding. That means simple processor implementation in terms of simple decoding. Consider in terms of your implementation. But there is the compactness. Another compactness is there or not. That means the variable length. In variable length, we say that the instructions are variable in size. That means some instructions have 1 bit as your app code and 4 bits as your app code or 8 bits as your app code. It is variable length. So in every case, whether your hardware is able to implement those instructions or not, so that gives the compactness. So that is completely differ with the simple encoding. So in this compactness, so which one is the better is choose by the designer as a designer. So this compactness are in variable length. The 86 ISS have the variable length instructions as said, but it saves memory, but huge headache to implement because it requires more functional units than the simple encoding. So in simple encoding, it may simply use the registers and your ALU, but whereas it may require a lot of functional units, So most processors today, the internally used fixed length micro encoded instructions, including 8086 for the simplicity purpose. So this is the RISC implementation concern of your ISA. Another concern is the implementation concern of this instruction is simple instruction management. That means no register memory instructions. If register memory instructions means it takes the complicated one. So simple instruction management means if it use only the register to register instructions, then all the operands will be available in the register itself, right? These things that get micro coded this, but this is deterministic latencies are key reasons for this the simple instruction management. The reason is all the operands R1 is equal to your R2 plus your R3, all the operands are in the registers itself, so they simply go and fetch the operands from the registers and perform the operation. So the time taken to fetch the instruction from these registers is constant, that deterministic. So that is every instruction finished within the same time, making like R1 is equal to R2 plus R3, or R1 is equal to R2 minus R3. So every instruction try to take the same time and making instruction scheduling much easier. So that is another concern, simple instruction management. But if it is a register memory, means you write R1 is equal to your R2 plus your R3. In that case, what happens for the second source? It must go to the main memory. So CPU first go to your register. If it is not there, from there it goes to your memory. Identify if memory size is, identify the element from there and fetch back to execute. It takes a lot of time. So that is not simple one. So simple instruction management means if it is using the register to register, then that is a simple instruction management. So instructions with multiple the exceptions are difficult in this case. Another concern is for register memory instructions. As we said, an instruction may trigger both arithmetic expressions and your memory exceptions. Arithmetic exceptions and memory exceptions. How in arithmetic, if you write that 2 divided by 0, what it leads? If it is right 0 divided by 2, what is? So in that case, which one is the exceptional one? And for the ISA implementation concerns, another concern is how much hardware requirement is required, more or less registers. So in terms of the programmer part, programmer says that if more registers are there, then the program can be executed fastly. But in terms of a hardware, if more registers are there or more registers are not always good. Once the register file is too large, suppose if I am using, instead of I'm having the total R1, R2 up to R16 registers. Instead of that, if I use only 4 registers, so searching 4 registers is easy in this register file. In this register file, if I am using 16 registers, it takes much time to search the register. So that is one. If more registers are there, searching for them and locating those registers is difficult. I mean, take much time. So once the register file is too large, accessing it will be slow. And another concern is in terms of the condition code. So in condition codes, or we use flags, many instructions have the side effects with these condition codes. That is, add has the carry over bits or carry in bits like that, and the selection of condition or flag registers affect the instruction scheduling. So this is the some of the concerns to implement the ISA. What is one is instruction selection, then the addressing modes, then the number of hardware parts and the depending codes, as well as the encoding and decoding purpose and the compactness one. So comes to the programmability, second compatibility. I mean, the second design issue, that is programmability. Okay. The first one is implementation, that is hardware. Then programmability, it is in terms of the programmers. In programmability, so well, at this moment, you may think that 8086 is a horrible, as it have variable lengths and have complex register memory instructions. Have we seen? We have seen the previous example. In the what you call the ISA classification based on the operands. There we have seen the register to register instruction and register to memory instruction part there. And if it is variable length, then it have the complex register memory instruction that we have seen, right? So, but programmability is also very important. Programmability is also very important. So, for the programmability of your ISA, before mid 80s, programmability is nearly the most important design issue of your instruction set architecture. So in 1960s to early 70s, the code was mostly hand coded, but later from 70s to early 80s, most code was compiled. Means the softwares are developed to translate the high level language into the machine level language, but hand coded was better compared to this compiled one. So this CISC ISA that provides the register memory styled instructions and many special instructions for the special use cases. Therefore, the CISC ISAs were early winners in up to 1980s. But after mid of 80s, the programmability becomes less important for ISA due to better compilers. That means from mid 80s to present, most code is compiled and almost as good as your assembly. So why means the optimizing the large amount of code is too difficult for the human. So from 1980s, the RISC, before that CISC was there, from 1980s, the RISC ISS made a successful comeback in 21st century, partially as the programmability becomes less important. So note that programmability is less important today only for the instruction set architecture, but not for the programmability. The programmability is still very important in fight among the CPUs, GPUs, FPGA, ASI architectures and the processors, and is still very important for high level languages. So, and the third feature of your ISA, or third concern of your, design part of your ISA is compatibility. Compatibility means the backward compatibility. Backward compatibility means it will never abandon the existing code base for backtracking or backward. So it is extremely difficult to introduce a new ISA based on this backtracking or back compatibility. So the alpha failed, for example, of this extremely difficult to introduce a new ISA for the alpha failed. Then IA64 is done, and the best solution may not win the alpha, and the IA64 are not the best between that. So this 8086 most popular for this compatibility of your backward compatibility, but is the least liked one. So the extensible for this for the future, it is hard to think ahead, and but ISA tweak may buy 5 to 10% of today. So the some 10 years later it may buy nothing, but it must be implemented. So these are three basic concerns of your CISC, so which leads to a good ISA in terms of implementation, ease of programming, and future compatibility. So based on this discussion, based on ISA good or bad, which leads to good or bad of your the ISA, the CISC and RISC came, as we said, that the debate ran from 1980s, early 80s through 90s. Now it is fairly irrelevant, but we'll just talk about the CISC and RISC in this case, right? Despite of the debates in this decade, the Intel and the DEC compact, they use this. They have tried to switch from CISC to your RISC path. So the research in the late 70s to your early 80s, which led to your RISC, means transforming or switching from CISC to your RISC. So there are many the research done by the authors John Keek and the Peterson, Handy. This John Keek Peterson done on the IBM architectures in mid 70s. Then the Patterson did the research on the Berkeley the RISC-1. Then Hennessy did the research on MIPS, and now in 1985 the Operand ARM2 came into the picture. So let us see the variable length instructions CISC basics, what happens there. So this is the VAX ISA is the 32-bit ISA. The instructions could be huge, up to 321 bytes, and 16 the general purpose registers are used to execute these instructions or implement and programmability purpose. But they operated on data types from 8 to 128 bits on decimal numbers and the strings by this architecture, and they are orthogonal. That means they are orthogonal in terms of the instruction, that is memory to memory. So all addressing modes are supported for the CISC. So that is, it may be the register addressing mode, direct addressing mode, indirect addressing mode, immediate addressing mode, auto-increment, auto-decrement, scaled one, your indexed one, memory indexed one. So all kind of addressing modes are supported by the VAX or the CISC architecture. So this orthogonal ISA supports all addressing modes, that is the instruction types, and the addressing modes are the orthogonal independent one. So hundreds of special instructions are introduced in this CISC to execute the special purpose or the specified instructions and the operations. And it is simple for compiler, but hand coding was very common in this CISC, the architecture, CISC instructions, ISA instructions. So an instruction takes more than 10 cycles to execute in CISC. Another one is 8086 CISC. Here it is using variable length one, that is 1 to 16 bytes, whereas your VAX used up to 321 bytes and 16 general purpose register. Here it used 1 to 16 bytes. The 8086 Cisco ISA, CISC ISK. So this architecture is used, our instruction set architecture is used to implement the floating point operations. To implement the floating point operation, they use the stacks which are inside the CPU itself. So these stacks are used for implementing the floating point instead of the registers, right? And there are two operand instructions only. These variable length instructions are two operand instructions, somehow similar to your accumulator, and they follow the addressing modes, register to register and register to memory support. whereas your VAX is memory to memory support that covers all the addressing modes. So, and this 8086 CISC has the multiple instructions for one task, multiple instructions for one task. So that is example, it can use the increase R11 and add R11 plus 1. So the operation is same. The operation is same. So increment the register by 1. Here add the register by 1. Do the almost the same thing. But usually one generic instruction that can do the task with the slower speed, because it needs to decode and execute. It takes slower speed compared to this one. This one is the faster one. So it has this, CISC has the special instructions optimized for this special task that live for the functional application, and it is scaled addressing modes. It uses the scaled addressing modes besides the common ones. Okay, and it has the extended many times like MMX, AMD 64. So the extension happened, and the Intel is used instead went for the IA64, which was not very successful, and then started using the CISC instruction. So then, we talk about the MIPS ISA, that is the RISC part. So this MIP multi, that means it used the what is the fixed length instruction, that is millions of instructions ISA. It follows the microprocessor without interlocked the pipeline stages, although the interlocked is back around in 2002. So they uses the MIPS RISC uses the 32-bit long instructions, that is fixed, and use the register to register operands mode, operands only. So must explicitly load operands from memory into registers before using them. So that is the concept used in MIPS, and they use the register indirect addressing mode, direct addressing mode, immediate, displacement, and index the addressing modes. So these addresses are stored in registers, as instructions are not long enough to hold 32 bits or 64 bits addresses. So also revised many times. This MIPS ISA RISC is also revised many times to evolve to 64 bits architecture and include modern features like single instruction multiple data. So a very popular academia teaching of your instruction set architecture is MIPS RISC one. The another processor is ARM. So this ARM is also use the register to register operands only, and it supports the register indirect, immediate, direct, and auto increment and decrement displacement addressing modes of this ARM RISC. Similarly, this the RISC V, it also supports the register to register addressing mode only. So only memory access instructions use the memory addresses, and it uses the PC relative. It supports PC relatives and register offset, that is displacement and absolute addressing modes. It uses 32-bit, 64-bit, and 124-bit fixed length instructions. And 32-bit integer registers and 32-bit floating point registers are used to implement the operations. So RISC V has the modular design to allow for extensions like base RISC V have the mostly integer instructions. The extension of that one support the floating point operations and automatic increment and decrement part and single instruction multiple data etc. instructions part. So finally, see the comparison CISC versus RISC. If you see, CISC supports the registers and register memory, like memory or accumulator and stack operands, whereas your RISC use only register to register operands. It is complex in addressing modes, but here mostly the simple addressing modes are used. Whereas in CISC use the variable instruction length, here it uses the fixed instruction length. CISC may have an instruction for any operation. Sometimes even the duplicate instructions will be there, as we see that the increment of your R11 or add the R11 with 1. So that one. So it is limited number of instructions will be here. The instructions requires variable number of cycles to execute, but whereas the instruction mostly takes the uniform cycles to execute. And here most spend a lot transistors and control logics, but here can spend a lot of transistors and registers itself. It leaves the complexity of the programs to hardware, whereas the RISC leaves the complexity of the program to the software. So with this, let us see the example of this in the next class.